Let's begin by exploring the fundamentals of Ohm's law and understanding what resistance really means in an electrical circuit. Along the way, we will consolidate our understanding of voltage and current. Voltage and current are often confused, but it's important to understand they behave differently in a circuit. Voltage is the electrical potential difference between 2 points, and it doesn't actually travel through a component like current does. Instead, voltage exists across the terminals of a component, creating the push that drives current to flow. So, when we say voltage doesn't go through a component, we mean it's not something that moves along the circuit path. Rather, it's the energy per coulomb that causes the electrons, or current, to move through the component. Understanding the difference is key to fully understanding electricity. To help make the invisible forces inside a wire easier to understand, we can compare them to something more visible, a mountain ski resort. The way skiers move down a mountain follows the same basic principles as how electrons move through a circuit. This analogy gives us an intuitive way to picture the movement and behavior of electrons by imagining the slopes and paths skiers take, which can help clarify how electrical currents work. Voltage is the potential difference between 2 points, acting as the work done per unit charge. To understand this, think of voltage as the vertical height of a mountain in a ski resort. The taller the mountain, the more energy you are given. Electric current is basically how fast charge moves past a certain point, measured in coulombs per second. Imagine a ski resort where the skiers represent electric charges. The current is like counting how many skiers pass a specific flag on the slope every second. So, current is not just about movement, but the actual flow rate of these skiers, or charges, through that point over time. This helps us see current as the flow itself, which is clearly shown in the formula, where current equals the change in charge divided by the change in time. Electrical resistance opposes the flow of current through a material. In the example we're using, resistance is like the trees, bumps, and narrow areas on a ski slope that make it harder for skiers to move. Even if the mountain is very steep, which represents a high voltage pushing the skiers down quickly, having lots of obstacles, or high resistance, will slow the skiers down significantly. This shows how resistance affects the flow of electrical current by making it more difficult for charges to move through the material. Think of the battery or cell as the ski lift, which adds energy to the system by giving skiers potential energy, just like the battery provides electromotive force. The height of the mountain represents the voltage or potential difference, showing how much energy is available for the skiers to use as they go down. The rate at which skiers come down the slope is like the current, indicating the flow of charge carriers through the circuit. Finally, obstacles like trees and moguls on the ski slope represent resistance, which slows down or impedes the electrons as they move through the circuit. This comparison helps connect familiar physical experiences with the principles behind electrical circuits. In a real conductor, resistance happens because electrons, which carry charge, bump into the vibrating ions that make up the atomic structure. These collisions slow the electrons down by taking some of their energy, kind of like friction. This energy loss is what we measure as electrical resistance. To make this easier to understand, imagine electrons as skiers navigating down a slope filled with rocks and trees. Just like skiers get slowed by obstacles on the path, electrons get slowed when they collide with the atoms in the material. This interaction at the atomic level creates the resistance we observe in conductors. Resistance is calculated by dividing the potential difference, or voltage, by the current flowing through the circuit. Voltage is measured in volts, current in amperes, and resistance in ohms. This relationship is also expressed as voltage equals current multiplied by resistance. Ohm's law highlights that the current through a conductor between 2 points is directly proportional to the voltage across those points, as long as the physical conditions, such as temperature, stay constant. This means if you increase the voltage, the current increases proportionally, assuming resistance doesn't change. Imagine we have a circuit with an unknown resistor, and we gradually increase the voltage. When the voltage reaches exactly 1 volt, we observe the current flowing through the component. If the current at that moment is exactly 1 ampere, then by definition, the resistor has 1 ohm of resistance. If it took 100 volts for 1 ampere to flow, the resistance would be 100 ohms. The resistance in ohms of a component can be thought of as the voltage required for 1 ampere to flow through that component. To find the resistance in a circuit, we can't measure it directly. Instead, we measure the current flowing through the resistor, which we call the flow, and the voltage across it, or the push. Using an ammeter, we measure the current passing through the resistor, and a voltmeter helps us measure the voltage across the resistor. Once we have these 2 values, we can calculate resistance by dividing the voltage by the current. An ammeter is connected in series, meaning the current flows directly through it, and its job is to measure the current passing through a specific point. For the ammeter to work correctly, its internal resistance needs to be as close to 0 as possible so it doesn't slow down the flow. Think of it like skiers on a slope. The ammeter shouldn't slow them down. On the other hand, a voltmeter is connected in parallel or across the component it's measuring to capture the potential difference between 2 points. Its ideal internal resistance is infinite to ensure that it doesn't create a new path for the current, which would be like creating a different route for the skiers and altering the flow being measured. When we plot voltage against current for a conductor that follows Ohm's law, we get a straight line that starts at 0. The key point here is that the steepness of this line corresponds to resistance. If the slope is steeper, that means it takes more voltage to push the same amount of current through the conductor. So, the slope directly reflects how much the conductor resists the flow of electric current. If you found this presentation helpful, I encourage you to visit physicsib.com. It offers a well-organized, interactive course designed to guide you through the materials step by step, making it easier to understand and apply the concepts we've discussed. This resource can support your learning by providing structured lessons and practice opportunities tailored to your needs. If you found this presentation helpful, please consider liking and subscribing for more content like this. For a more structured and interactive learning experience, you can visit physicsib.com, where additional resources and courses are available to support your studies. Thank you for your time and attention.